Welcome everyone to our next video here, in which we'll continue to explore some of the basics of reverse engineering using Ghidra. In this video, we're going to take a look at structures. So we'll define a few structures that use both the stack and the heap in order to store the data for their members. We'll compile the program, disassemble it, and then look at the disassembly as well as the decompiler output. You'll be able to, by the end of this video, then recognize some of the nuances and how these structures are created or interpreted by the compiler, how to identify and analyze them at a low level, and we'll also see a few discrepancies with Ghidra output here. To get started then, we have a very straightforward program that you can find in the link in the description for this source in GitHub. I've defined three structures. I've called the first one an align structure. Then we have two padded structures, and I'll talk about the padding here in just a moment. Now, normally when defining structures in a C program, we don't necessarily care about the particular layout. We allow the compiler to handle that for us and translating it to machine code. But when reverse engineering, we need to understand a little bit deeper. And so we're going to look at the total size of these structures as well as the size of the members, and then how much memory is actually required for these structures when they're created. The alignment then has a great deal to do with that, and that for the most part, the compiler is going to strive to align the structure to 4-byte boundaries in terms of memory. And so you'll see that at times when you use members that don't facilitate that alignment, that the compiler will add some padding in order to facilitate the CPU and reading and writing to memory. So let's look at our first structure here. We have what I call the aligned structure. And the reason that this is aligned is because we have these four members, integer A, which is 4 bytes, followed by a short B, which is 2 bytes, and then two chars, which are a single byte each. So these 4 bytes will line up nicely. We'll then have 2 bytes followed by 2 single bytes. So all of this maintains a nice 4-byte alignment. If we look at the size of the structure, we'll see that we have 4 plus 2 plus 1 plus 1, so we really need only 8 bytes on the stack or in the heap to facilitate the use of the structure. Now, if we move on to the next one, what I'm calling our first padded structure, and these are the only two that we'll actually look at in the program. This third one I've just added here to kind of demonstrate this concept of padding. You can see that for the first member, I created or I defined char A, which is a single byte. I then followed that with a short B. We need 1 byte for this char. We need 2 bytes for the short, which means that in order to maintain a 4-byte alignment, we could add, or the compiler will add, 1 additional byte of padding, which it will do here. That means that when we see this structure being used after we reverse engineer the program, we'll access this char at the beginning of the structure at an offset of 0, and then we'll access this short at an offset of 2. And we'll go through all of this here as we get a little bit deeper into the program. Following the short then, we have an integer C, that's 4 bytes, and that's now aligned after we have this padding to adjust. And we have a pointer, which is also 4 bytes, so that will follow these 4 bytes. With the padding then, we can look at adding the total size of the structure up, and we have 4 plus 4 plus 2 plus 1 plus 1, or 12 bytes. Right? Had we not recognized that padding, though, or the need for that padding, and we just simply added up the size of the structure based off of the member types, we would have come up with 11, which would have given us or made us 1 byte short. Now, again, we don't typically concern ourselves as developers for going through here and adding up the size of the structures because, again, we want to use syntax in the language that allows the compiler to worry about that. And you'll see that down here when we define these structures, that we don't malloc memory the size that we calculate manually. We use the size of and the structure in order for the compiler to determine the size and then allocate the memory appropriately as our argument for malloc. Now with our final padded structure, again, kind of a very similar layout in that we have a char pointer. This is going to be 4 bytes because it's a pointer, so don't let the char type there confuse you. All of our pointers here, and this will be a 32-bit program, will be 4 bytes. This will be followed by a single char, which will then be followed by a long X, which will also need 4 bytes. But because we did 4 bytes, a byte, and then 4 bytes, in order to maintain that 4-byte alignment, we need to have 3 bytes of padding here. So we would see that for this particular structure, we would add up again 4 bytes plus 1 plus the 3 for our offset plus 4, it would also need 12 bytes. Even though we're not using all 12 bytes, we're actually only using 9 bytes. Now in the program, again, a fairly straightforward program, and that I just instantiate these structures and then move some data into the members so that we can see as we're reversing them exactly what offset is being used. So how is the memory that's been allocated for these structures, how is it actually being utilized? I have int z with a value of 99 decimal or base 10. I'm only defining that in order to provide the pointer to that local variable here to one of our structure members. And then we're also going to be able to observe the difference in defining a structure on the stack, which is what you see being done here, versus a structure that is malloced or allocated memory dynamically, so memory in the heap, and then we reference the members of that structure that way. Now, aside from the memory coming from the stack or the heap, one of the more significant differences we'll see, again, in terms of reverse engineering, is that as we look at these members, because they're on the stack, it almost will appear, or it'll be much more difficult to recognize them as maybe not being local variables, because you'll see that they will just simply be offsets on the stack, and we are moving data into those locations. So we'll notice that here as we're reversing those. When it comes to these structures that are using dynamically allocated memory, what will happen then is malloc will return a pointer to the memory that was allocated. That'll be stored in our local variable, and we'll be able to observe that all of these members then are relative, some offset relative to that actual pointer, that base of that allocation. So it becomes a bit easier to identify the structure and the makeup of these particular structures, which is very similar to the C++ objects that if you haven't watched the video previous to this, we discussed kind of a very similar concept here. Okay, one of the last things that we'll do then before we move into Ghidra is just to look at how much space on the stack we need for all of this code that we've created. So we need 4 bytes for our local variable. We're going to need 8 bytes for this structure, so that's 12 bytes. We'll need 4 bytes for these pointers each. So we need 20 bytes of total space on the stack in order to facilitate these structures that we've created as well as a local variable. Next steps then is to go ahead and use the developer command prompt in order to compile the program. Once you've compiled the program, you can import it into a project in Ghidra, navigate to main, and we'll get started with our analysis there. If you're unfamiliar on how to do all of that, several of the videos before this have gone through that process there. So I'm trying to avoid being too repetitive in these videos. So let's move over to Ghidra now. Okay, so we're at main in our now our analyze program. One of the first things that we can look at is the prologue to the function, and we'll see that we have our push EBP, move EBP, ESP. So we've created the base of the stack frame for this particular function, which happens to be main, and then sub ESP 14 hex. That is, if you need to do the calculation between hex and base 10, you'll see that that's decimal 20, hex 14. And so that was the value that we had just previously calculated. So that all seems to add up. And one of the main reasons that I wanted to just reiterate that was because we are using some of the stack space for our local structure, for one of our structures, our very first one. Now, you'll notice in analyzing this code here that I have both the disassembly, which is where we're going to actually spend most of our time, and also the decompiler here. So we'll have two sources to kind of bounce back and forth of to analyze this program. Now, we begin, well, one other thing that I also have open is the disassembled view, and that's just to help us that if we need to select any of these lines, because maybe it's cut off and we're not able to see that, then we can select that specific instruction, and that'll show that instruction as well as the view around it. So that just helps with our display. Now, after the prologue, we can see that we move into EBP plus local 10, a hex value of 63, which would be base 10, 99. Now, that's the initialization of that local variable. I called that Z in the original program, so we could rename that. You'll notice if you highlight that instruction that we'll see the corresponding line here in the decompiler. There is the value 99 being moved into local 10. Now, it looks a bit like array syntax here, which is a bit misleading because it's not. It's just a local variable. Next thing we see is that we XOR EAX with EAX. So anytime you XOR a register with itself, that zeroes out the register. And then from there, we're moving EAX into local EBP plus local 18, EBP plus local 14. So that is actually how the compiler decided to handle the instantiation of the structure. Since I put the curly bracket with the 0, I was telling it that I want to zero out the memory once the structure is created, and that's just how the compiler decided to handle that particular step. This also means now that we know that at an offset of from local EBP plus local 14, EBP plus local 18, that is the space on the stack for that structure, right? Each one of these is going to represent 4 bytes, so that's 8 bytes, and we originally calculated, if we go back to our first aligned structure definition, that we would in fact need 8 bytes for this particular aligned structure. So that looks like that's adding up. Now, if you get confused with the local 18, local 14 convention, you can always hit the C key, which will clear the bytes, then hit the D key, which will disassemble, and you'll be able to essentially remove that variable name and get just the original or kind of raw offset value. So EBP minus 14 hex. If we need to do that to any of these other ones, we can do that maybe a bit broader, and then disassemble again, minus 10 hex, minus 14 hex, and you can see the actual raw offset value. Now, when it comes to the stack, typically the stack will grow from higher addresses to lower, which means then that the base of our structure, the base of our arrays, they begin at the lowest or the highest offset, so the lowest address. So minus 14 and minus 10, minus 14 then, that's the largest offset, which would result, because we're subtracting that from EBP, in the lowest address, so that's the base of the structure. So these two instructions are now zeroing out the 8 bytes for our structure, and this instruction here is moving hex value 2A into the first 4 bytes. So EBP minus 14 hex, it's saying at this location, dereference it, and we have a D word or 4 bytes worth of memory that we can use. Hex 2A, if we right click on that, you can go to convert. That's unsigned decimal 42. Again, if you go back and look at the original program real quick, then that was the value that I moved into that location. While we're here, just take note, we're going to move hex 1FF into B, and then char A and char B into C and D. We can use the undo feature if we want to undo our clearing and redisassembling, and that'll take us back. That's at least a quick way of getting back to using the default listing view here that provides us with the local instead of just the raw offset. So again, local 18 was used as then that largest offset. Right, and that's just, again, something that you can see represented here in how the default naming convention is used in Ghidra, minus or this having a larger value, which then represents a larger offset from EBP. If we move to the next instruction, then we can see that we have our hex 1FF being moved into ECX. Then we have CX moved into local 14. So CX is just taking the lower 2 bytes of that register. It's chopping off any bits that were greater than 2 bytes if we happen to have a value larger than a short, and moving it into local 14. So local 18 is the base of the structure. If we add 4 bytes from the base of the structure, we're now at a higher address, so a lower offset, and we're at local 14. From there, we're going to handle then the 2 byte values, those 2 chars. So we're moving hex 61 and hex 62, which is just simply the hex value, the numeric value of those ASCII characters. And we're now moving those into, and these get a little bit harder to see here, we're now moving that into an offset of local 14 plus 2 and local 14 plus 3. So again, if we had a 4 byte value at local 18, we added 4 bytes to get our short, we have local 14. Now to get to account for our 2 bytes for our short, we have to add 2. That gets us to our first char, and then another byte to get to our last char, so a value of plus 3. And that is how we can recognize those offsets. As I said, this can look a bit more like local variables. And so structures that are defined on the stack and use stack space can be a little bit harder to analyze. You'll also notice that all of these instructions here, even though we very clearly in our original source define that structure and move values into the members, that is not represented anywhere here in the decompiler output. And unfortunately, I don't know exactly why that is. So just something to keep an eye out for. And one of the many reasons, especially as anyone new to using Ghidra as a tool, it's important to, I think, to have and oftentimes reference both the decompiler and the disassembly window. Now, if we move on, we'll see that we push 8. We call this function here, which is actually malloc, and then we move EAX into local 8. So if we go back and take a look at our original program, the next thing that we're doing here is we are actually mallocing the 8 bytes of memory as determined by the compiler based off of the definition of our structure. And then we're going to use the base of that structure, that memory, in order to dereference those members and move data in and out. In this case, we're just assigning data. So we can see that here, push 8. So that's our argument that was determined through the compiler, through looking at the size of the structure. The call then to malloc, and because malloc is going to return the address that was allocated for the structure in the EAX register, that is now being moved into local 8. This also lines up much nicer here with our decompiler output, although again, this seems to be a bit misleading here in terms of the signature of this function. Once we move into local 8, we have now in local 8 the pointer to that structure. And the pattern that you're going to see now is that we're going to continuously move local 8, and this is local 8 here, into EDX. We then dereference EDX and move data into that location. So we know that this the first 4 bytes of this memory, because of this syntax right here, are going to be used for that value, hex 2b. This is also indicated here in the decompiler output. And again, if we go back and we look at our original source, we have the hex value, or the base 10 value 43 moved into A, then we're moving 3 into B, then we have our char C and our char D. So it's the exact same structure, we're just in heap memory instead of on the stack. Okay, so let's go back to Ghidra. We now move 3 into EAX. 3 then is, local 8 is moved into ECX. We now dereference ECX at an offset of +4, and we move AX into that location. So we can see that here in our disassembly window as well. So very similar process that we saw previously, handling for the potential overflow, cutting off any of the bits beyond in the upper 2 bytes of the ECX or the EAX register, and then moving that into an offset of +4. So we now know, again, not only did this first instruction make it clear that we have 4 bytes available for that member, but now we are referencing ECX +4, so we've moved to an offset 4 bytes, from the base of the structure. Okay, the next thing you'll see again, local 8's moved into EDX, and then EDX will be dereferenced at an offset of +6, and we move a hex value of 63. So that's just the numeric value for our char. This is a byte pointer, so we know we only have 1 byte here. So we have an offset of 0, we have an offset of +4, and then we have an offset of 6 and an offset of 7, right? And that's, again, you're just seeing that same pattern emerging here. Go back to the original source, and let's actually go back to where we defined that. And I said that we would have an offset of 0, an offset of +4, an offset of +6, and an offset of +7. So again, we saw the differences there. Looks a little bit harder, a little less clear when it's defined on the stack, a little bit clearer when it's defined in the heap. But it still all lines up in terms of how that structure was actually defined. Finally, we're going to look at our padded structure, right? And what I'm telling you with this one is that we're going to need 12 bytes total, which is C and hex, and that we're going to have an offset of 0. We're going to have a byte for padding, then an offset of 2, an offset of 4, an offset of 8. So let's take a look at that in Ghidra. There's the push C or 12 hex, or C hex or 12 bytes base 10. That's being pushed for the call to malloc, and then that's being stored in local C, which we can see here. Again, very similar now to the previous structure that was defined. So that looks good, right? We've got the 12 bytes that I said we would have. Now from there, we move local C into ECX, we dereference ECX and move hex 65 into that location. So this is telling us that at that address that we just allocated memory for, we can only use a byte's worth of memory, which is this syntax right here. We now move into EDX hex AA, we move our pointer into EAX, and now we're dereferencing at an offset of EAX plus 2, right? So we went from being at the base of the structure. If we were to write to the second byte, we'd have an offset of plus 1, but we skipped that byte for padding, so now we're at an offset of plus 2. Okay, we dereference this. We know that that was a short, so we have a word pointer, so 2 bytes worth of memory, and we're moving DX into that location. So again, this pattern that we saw of moving the value into the full 32-bit register, EDX, and then only moving the lower 2 bytes into that location. From there, we move our local back into our pointer to our structure into ECX. We now dereference it at an offset of plus 4. This is going to be for our integer. So we can move the value into ECX plus 4. And again, we have a full 4 bytes of value there. We now move local into EDX again. And this time we're dereferencing at an offset of plus 8. Right, and so that we had to move 4 bytes ahead because the last member was in fact 4 bytes. It was our integer. We move EAX into this location, and only thing that's happening here is that we're using LEA, load effective address, in order to get the address of EBP plus minus hex C instead of getting the contents that's stored in that memory location. And the reason that we're doing that, if it wasn't clear when we initially looked at the program, was because we defined this local variable int z on the stack, and we used the address operator, the ampersand, in order to get the address of that value, that local variable, instead of its actual value. So that's just, we're just seeing that now in the disassembly. After that, we zero out the EAX register for our function's return, and then we have the epilogue of our function. So that's really all there is to it. As I mentioned, though, we didn't look at or instantiate the second padding structure, but hopefully you get the kind of get the idea behind how the layout of the members and adhering to this 4-byte boundary for alignment can either lead to nicely aligned structures or structures that may need a bit of padding. And so as a developer, you can also kind of use this to your advantage to make your structures a little bit more streamlined or rely upon optimizations within your compiler. As a reverse engineer, it's important to understand that as well, because you might have more memory than you think you need based off of program analysis, simply because there's some padding that's that has been applied there. You've also learned a little bit more about the difference between how these structures look on the stack and in the heap, and that those structures defined on the heap become a little bit easier to identify because they are generally going to use offsets from the base of the memory allocation. So we had our padded struct here, we had offsets of 0, 2, 4, and 8, and as we saw during program analysis, we had the base of our structure, no offset needed, then 2, then 4, and then 8. So again, it makes it a little bit clearer when doing the program analysis or the reverse engineering that this is a structure. This memory is all related because we keep going back to the base of the allocation and then referencing specific offsets. That helps us define those members. Now, when we reverse engineer, one last thing, we don't necessarily know the type. We have to oftentimes infer that from the analysis of the program. So we know that this value being moved into this location, it's a 4-byte value. This seems to represent, in most cases, an integer, and so that's likely what it is, but it's not as clear. When we look at the fact that we've loaded an address into EAX and we move that value into EDX plus 8, well, this makes it appear that it is likely more of a pointer type. Now, that can also be a bit confusing because sometimes we'll see that LEA is actually used for basic arithmetic and not always just to obtain a pointer. So there's plenty of gotchas and nuances as you continue to learn more about assembly and what compilers do to high-level languages as they compile them, turn them into machine code, and then we try to reverse that machine code back into something that's a bit more human readable. Anyways, hope you enjoy learning a little bit more about the internals of how structures are represented, and I look forward to seeing you in the next video. Thanks.